Welcome back to another lesson of functions and applications, where today we are looking at modeling quadratics now that we've been working with them quite a bit, and also how to solve them using their graphs. So today we're going to be graphing a lot and looking at graphs. And our learning goal is to use quadratic relations to explore real-world applications using technology and to interpret the results. So my focus today is not as much for you to graph, although we will practice that a bit. But I mostly want you to try practicing graphing with technology and analyzing the graph based on real-world applications. So what the graphs could mean. So here, our first problem is a model rocket is launched from the roof of a building. The height h of t in meters at any time t in seconds is modeled by the function that's given to you. So h of t is equal to negative 5t squared plus 15t plus 20. So first you're asked to graph the movement of the rocket using a table of values. So take a moment here to pause and fill out the table of values. So you should you can use a calculator here or your graphing tool, but you should have gotten 20, 30, 30, 20, and 0. And I'll leave a star here for now because there's something in the middle there that's going to be important for us. So now when we want to graph it, so I know that my time is all positive and my heights are all positive. So when I'm setting up my Cartesian plane with just freehand, or let me draw this again. Try to use straight lines. Here I'm going to have time in seconds, and over here I have height in meters. And so for my time, I only want to go up to 4. So 1, 2, 3, 4. And for my height, I see that I go to about 30, maybe a little bit more, but not significantly more than 30. So maybe I'll just do 35 as my max. So I'm going to do 5, 10, 15, 20, 25, 30, 35, approximately there. My scaling is not the best. If you're using grid paper, you get a better scaling, so definitely try to use that. And so here, if I graph my points, I have 0, 2. At 1, we have 30. At 2, we have 30. At 3, we have 20. And at 4, we have 0. And so recognizing that this is now a parabola because it's kind of its shape, we see that our parabola is going to go something like this. And the star is actually this point here where we reach our maximum height. So looking at this graph now, this is showing us the movement of this rocket through the air. So it goes up, reaches its maximum height here, and then it starts to go back down. And this all happens over 4 seconds. So the question you're asked of when will the rocket hit the ground? When the rocket hits the ground, its height is 0 because that's the same as the ground. So we are essentially looking at this point over here, which is going to give us that the rocket hits the ground at time equals 4 seconds. And so over here on the bottom, I've included the graph using Desmos. So it's a more precise graph than mine. And that same star point is now here, where we see that at 1.5 seconds, we have reached our maximum height, and it's 31.25 meters. And you're asked what other information can you determine from the graph of the rocket's motion. So having this graph now, if I ask you the height of this rocket at any time between 0 to 4, you can, from the points, be able to tell me. I may also ask you The height of the rocket is 25 meters. At what times does this happen? Because I hope you've seen now that this will happen at two times, once on the way up and once on the way down. And another key thing about this graph is when the rocket is at time zero. So before the rocket has launched, we're actually not on the ground. There is a height of 20 here, which is 0, 20. So that tells me that my rocket was launched from a height of 20 meters. So its initial placement was 20 meters above the ground. And then it moves up into the air and comes back down to land at time uh, 4 seconds. So you've been working with, and you may have noticed even in my lessons, I switch between expression and equation, but an equation is pretty much an expression with an equal sign. So here, we have x squared plus 7x plus 10, and this itself would be an expression, and adding that equals 0 gives us an equation. Now, for it to be a quadratic equation, it needs to be a polynomial that has a highest degree of 2, and it has that equal sign. So, in our example of the rocket, when the rocket hits the ground, its height is 0. So we're essentially solving the equation where its height, remember this is just h of t, the expression for h of t, or the function h of t. So we want to set this equal to 0 in order to find the correct time that gives us the height at 0, which is also the time when the rocket has landed. So here, try first, solve for h equals 4. Or, sorry, for h at time equals 4. So if you tried that either with a calculator or just on your own, the way I did, you should have gotten 0. And so that actually works. And what it tells us is essentially what we found out on this page, which is that when the time is 4 seconds, the height of the rocket is 0. So that could either be that it has landed at that time or is already on the ground at that time. Um, so in our example, because it's a quadratic function, uh, it's, and if we look at the parabola, this is the point that we care about. So when time is 4, our rocket has landed on the ground. This is also called the root of an equation. So the root is pretty much a number that when you substitute it in for your variable, it makes your equation a true statement. So in our example, when we had h of t is equal to 0, because we wanted to know when the rocket hits the ground, we wanted to find values of t that fit in our equation. So we saw that up here where when we substituted the value of 4, we actually got that same 0 that we were expecting. So based on the graph now, we're going to try to answer the following. So take some time to try to answer it on your own. So our first question here is, what is the starting height of the rocket? So you should have your graph side by side. So just take a look at it here, and then we're going to answer here. So the starting height was 20 meters, and that was when time was 0. So this was shown on the graph precisely over here. And it is actually the y-intercept here, because it's at, or not x, actually t is 0 because time is 0. So at the starting time, t equals 0, we have our y-intercept and it's 20. You could have a rocket that starts on the ground where it at time 0, your height is also 0, but it's not the case for this rocket. And where is this shown in the function? If we go back to our function here, I hope you see that if we set t equals to 0, this is 0, this is 0. So really, this is our c value. And this actually works for any quadratic function. If you set x to be 0 to find the y-intercept, your y-intercept will be c, because that's the only term that will be left. And what's the maximum height the rocket reaches or achieves? The graph above here showed us it was 31.25. And please don't forget your units when you're writing these. So 31.25 meters. Now you've seen the height of a rocket modeled by quadratic function. And at the start of this lesson, I shared a link with you on the height of a water balloon thrown by a group of students who were actually studying the quadratic function. And as we continue, I want you to also consider other real world problems that can be modeled with the quadratic function. And this is related to your discussion post that you will be completing as well. So, continuing on, we're going to take a quick break from the application just to see a little bit of a check here. So, when we are factoring, we sometimes want to check our answer as well, and that always helps with interpretation of our results. So, consider this equation, x squared minus 8x plus 12 equals -3. To solve this equation, we need it to equal 0. We need one side of this to be equal to 0 so that when we factor, it'll make it a little bit easier. So we need to actually move this -3 over. And so if you do that, which you can achieve that by adding 3 to both sides, and this will be simplified to 8x plus 15 equals 0. So I encourage you to take a moment to graph this using Desmos now. So here, I've just, for now, written x squared minus 8x plus 15. So to get the roots of this equation, we want to essentially look at when this parabola is equal to 0. And I see that this happens at point 3 and 5. So my roots are 3 and 5. Had you changed this to equal 0, you would have received two straight lines, two vertical lines, which are equal to x equals 3 and x equals 5. And that's essentially telling us that that's the answers to this equation. So you would have got x equals 3 and x equals 5. So I'll close my Desmos for now. So now we want to check, especially because we altered our original equation, we want to check that it actually works. So when we do the check, we are also using our original equation. In case you made any errors throughout as you were solving, you will be able to check that using the original equation, which nothing has been changed. So in our original equation, on our left side, we have x squared minus 8x plus 12. And first, let me check for x equals 3. So x squared minus 8x plus 12. Let me just double check that. Correct. So now I'm going to substitute in the value of 3 to get 3 squared minus 8, 3 plus 12. And continuing on, we get and this is equal to -3. And the right side of my equation was actually just -3 to begin with. So the right side, we're just going to write equals -3. And now, to put this all together, we'll be introduced to a little bit of a math symbol. You might have seen this before. We say, because the left side is equal to the right side, so that means the equation holds true. And that goes back to our definition of roots of an equation. So because the equation holds true, then x is -3. So that solution works. Or, oh, sorry. X is not equal to -3. X equals 3. That's the value we substituted. So yeah, don't get confused with that. We were doing this check to verify that our root was 3, and we were able to do that. So now take a moment and check for our second root, which is x equals 5. So similarly, you should have got -3 on both sides as well. And again, we will write our because left side is equal to right side, therefore x is also 5. So our two roots hold true. Now let's look at another question, and this is a word problem, and it's given you determine the point of intersection of the function f of x equals x squared minus 8x plus 12 and g of x is equal to -3. And I hope those two are a little bit familiar to you because let's go a little bit up. They are actually the two values or the two expressions we saw here. So here it's asking you to determine the point of intersection. And if we remember point of intersection from previous years, we know that that is the same thing as setting the two functions to be equal. So we want to find out an x value such that f of x is equal to g of x. So at that x point, both of their outputs are the same. So if you have, for example, a parabola going like this and a line that is going to intersect it like that, these would be your 2 point of intersections with the parabola. So for the same x values, they also have the same y value. So setting now these two equations to be equal, we get x squared minus 8x plus 12 is equal to -3. And that's the problem from the last question. It's exactly what we began with. So now we want to solve this equation. So we want to find an x value that holds true for this. So again, we still have to do the same thing as above where we factor, or where we rearrange first to factor. So minus 8x plus 15 equals 0. So now take a moment, try factoring this using the methods we've learned. And you should have gotten x minus 3 and x minus 5 is equal to 0. And this was the graph that we saw above as well. So now, how does this factored equation relate to the graph and the roots that we saw from before? Essentially, this factored equation is telling us that we are multiplying two numbers so that their product is equal to 0. And what that means is either that this term has to be 0, so 0 times the second bracket is equal to 0, or the second bracket has to be 0, so that when you multiply by 0, you get 0. So if this one is 0, for this to be 0, we need x equals 3. And for this to be 0, we need x equals 5. And precisely if we look at the graph, we see that at point 3, x is 3, and at point x is 5, we do get that output value of 0. So now let's look at both of those graphs now function just on their own. So the purple parabola is our x squared minus 8x plus 12 function, and the green line is the g of x is equal to -3 function. And you can see that they do intersect at x is 3 and at x is 5. And the output value at which they intersect is -3, which was the same value as g of x. So I hope you see the connection between these two, as well as what we saw in this problem where we got the two vertical lines of x equals 3 and x equals 5. So now let's apply that to a word problem. The population of an Ontario city is modeled by the function p of t is equal to 0.5t squared plus 10t plus 300, where p of t is the population in thousands and t is the time in years. And a specific note here that t equals 0 represents the year 2000. So what that means is t equals 1 is 2001, and t equals 20 is 2020. So first, what was the population in the year 2000? So that is actually just t is equal to 0. So try this on your own, see what you get for the population. So if you substitute the value of t equals 0, you see that the first two terms are just 0, so you're just left with that c value, or your y-intercept, or 300. And specifically for this question, p of t is the population in thousands. These units are very important in word problems because your answer is not just 300. And when you write your concluding sentence, which you should be doing for all word problems, please make sure you are including that unit here. So I will write my conclusion of in the year 2000. So we're not looking at t equals 0. I want to give it some meaning. So in the year 2000, the population was 300,000 people because the 300 has that in thousands unit. Now, what will the population be in 2010? So for this one, we are, I need my equation one more time. So P of T, and I highly recommend you always rewrite the equation if you don't have it right in front of you for each problem. Okay, so here now, 2010 is 10 years after the year 2000. So if t equals 0 is 2000, then the year 2010 is t equals 10. And so we're actually finding P of 10 as so. Oh, and so we get 50 plus 300. So 450. But again, 450,000. So you would write, therefore, in the year 2010, the population uh or was, because we're past tense, was 450, and you can just write 1,000. That will work. Now, we're asked when is the population expected to be 1,050,000? So to do this, again, because right now we just want to look at the graphs, so we're just going to graph the original parabola, and now we want to also graph our horizontal line of y equals 1050 in order to get that population. So again, remember, because the population is in thousands, when we are doing this, when we are solving this, we have to get rid of those 3 zeros at the end. So the P of t will actually be 1050. And so we look at where these two intersect, and we see that they intersect at 2 points, but one of them is -50 and the other is 30. So we are not going back in time, so we will not be using the negative value. It will be inadmissible here. So we only look at the positive value here of 30. But keep in mind, its t is 30. So when we're considering the year, we have to add 2000. So in the year 2030, the population will be 1,050,000. You would have achieved this also if you set the two equations to be equal. So I'll briefly show you that here. So let's write 0.5. And with Desmos, because it is based with x, whenever you see t values, just convert them to x for the graphing purpose. But just interpret your results as t. And if we set this equal to, and keep in mind, I have to zoom out my graph because these are bigger values we're working with. And you see those two vertical lines here as well for -50 and 30. And again, same explanation. We don't want to consider the negative value, so we only look at the positive 30. And so we bring this back into our word problem. So in the year 2030, the population will be 1,050,000. So that's our lesson for today. So we got familiarized with all the quadratic models, their graphs, and what the results could mean in real world applications. So for today's practice, I have some point of intersection problems as well as some of the word problems similar to the styles where we work today, so population and height. So please practice those while they're fresh in your mind. And as always, if you have any questions, please don't hesitate to reach out, and I'll see you all next class.